black holes get all the attention. They bend light, they trap time, they seem to erase matter from existence. But there are objects in the universe that are, in some ways, even stranger. Objects so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Objects that spin hundreds of times per second, sweeping the galaxy with beams of pure energy. They are called pulsars, and if you were to fall into one, what you would experience is nothing like falling into a black hole. This is a realistic simulation of what it would be like to fall into a neutron star pulsar. So, what is a pulsar? To understand that, we have to start with a star. Not just any star, but a massive one, many times larger than our Sun. For millions of years, it burns brightly, fusing elements in its core. But eventually, that fuel runs out. The outward pressure of fusion can no longer fight the inward crush of gravity. The star's core collapses in an instant. This catastrophic event triggers a supernova explosion, one of the most violent events in the universe, blasting the star's outer layers into space. But what's left behind is the real story. The core, crushed by its own immense gravity. The pressure is so intense that electrons and protons are forced together, merging to form neutrons. The result is a neutron star. Imagine an object with more mass than our entire Sun squeezed into a sphere only about 20 kilometers across the size of a city. The density is unimaginable. It's like the entire human race compressed into the size of a sugar cube. This is matter pushed to its absolute limit, a giant atomic nucleus floating in space. Now add rotation. Think of an ice skater pulling in their arms to spin faster. As the massive star collapsed, its rotation sped up dramatically. Some of these neutron stars spin hundreds of times per second. And here's the final piece of the puzzle. A powerful magnetic field. If the star's magnetic axis doesn't line up perfectly with its spin axis, something incredible happens. A pulsar is born. It acts like a cosmic lighthouse. The intense magnetic field funnels particles, creating powerful beams of radiation that shoot out from the magnetic poles. We're talking radio waves, X-rays, even gamma rays. As this stellar remnant spins at incredible speed, these beams sweep across the galaxy. If one of these beams happens to pass over Earth, our radio telescopes pick it up as a regular, repeating pulse of energy. That's why we call them pulsars. Some are so precise, their timing is more accurate than the best atomic clocks we have on Earth. They are nature's most perfect clocks. But we're not observing from a safe distance. In this journey, you are falling straight toward the source. From far away, the pulsar looks strange. Just a tiny point of light, but its gravitational influence is already undeniable. As you get closer, you see space itself begin to warp. The light from distant stars behind the pulsar is bent, stretching into arcs and rings of light, a phenomenon called gravitational lensing. But there's a key difference here compared to a black hole. There is no event horizon, no dark, shadowy sphere that marks a point of no return. The pulsar is right there, exposed. You are falling toward a physical object, a spinning, superdense ball of matter that you can, in theory, see long before you get anywhere near the surface. You enter the pulsar's magnetosphere. This isn't like Earth's gentle magnetic field that guides our compasses. This is the strongest magnetic field known to exist, trillions of times more powerful. Space here isn't empty. It's a storm of relativistic electrons, ionized plasma, and high-energy radiation, all trapped and accelerated by the magnetic field. Your body would immediately start to feel its effects. The electrons in your atoms would be twisted into new paths, destabilizing the chemical bonds that hold you together. Any electronics would fail instantly. Without some form of impossible shielding, the radiation alone would kill you in a fraction of a second. But for the sake of our journey, we'll imagine you're protected, and we continue our fall. As you get closer, your senses are completely overwhelmed. The pulsar's rotation dominates your view. This isn't a gentle spin. It's a violent, dizzying blur. The star is rotating so fast that light from its surface is warped by special relativity. The side spinning toward you is intensely brightened, its light blue shifted and boosted in energy. The side spinning away is dimmed, its light red shifted and faint. The result is a chaotic, strobing flicker, blinding flashes alternating with sudden darkness, repeating hundreds of times per second, a pattern far too fast for the human brain to even process. Time itself starts to warp. Because of the intense gravity, your clock begins to tick slower relative to the outside universe. For every second that passes for you, minutes, then hours, could be passing for a distant observer. But again, this isn't a black hole. Time doesn't stop. It's just overwhelmed by the sheer insanity of the environment. And now we come to the real danger, the force that makes a neutron star arguably even more terrifying up close than a black hole of the same mass. Tidal forces. Gravity gets weaker with distance. When you're near a massive object, the part of your body closer to it is pulled much more strongly than the part that's farther away. For a typical stellar mass black hole, this stretching effect, known as spaghettification, happens after you've already crossed the event horizon, hidden from the universe. But a neutron star has no event horizon. Its surface is right there. And because it's so small and dense, the gravity gradient is brutally steep. The difference in the gravitational pull on your head versus your feet would become enormous, almost instantly. You would be stretched with unbelievable force. Your bones would snap. Your tissues would tear. Your cells would rupture. Before you even get close to the surface, you are torn apart, not just into pieces, but into a stream of individual atoms. You aren't falling onto the pulsar, you are being disassembled and fed to it, one particle at a time. But what if, by some miracle, a fragment of you could survive this process and witness the surface? What would you see? The surface of a neutron star is called the crust. It's not a solid in any way we would recognize. It's a bizarre lattice of atomic nuclei crushed together into exotic shapes that scientists have nicknamed nuclear pasta. There are layers of spaghetti, lasagna, and other strange formations of nuclear matter. The gravity is billions of times stronger than Earth's. The landscape is incredibly flat. Any mountains would be no more than a few centimeters high, yet they would be denser and heaviest if you were to hit this surface. You'd be traveling at a huge fraction of the speed of light. There wouldn't be an impact, there would be annihilation. Your matter, already reduced to a stream of atoms, would be utterly obliterated. The crushing pressure forces your electrons into protons, turning everything into a sea of neutrons. Your body ceases to exist as matter defined by chemistry. It becomes degenerate matter, completely indistinguishable from the star itself. You are not consumed or destroyed in the way a black hole seems to do. You are simply added. Your constituent particles become another infinitesimal layer on this incredible object, a star that will continue to spin and shine for billions of years. So let's compare. A black hole, with its event horizon, erases things from our visible universe. Information seems to be lost forever. A pulsar does not. Everything that falls into it remains part of the star, part of the cosmos, just transformed into its most extreme possible state. There's no horizon, no mysterious disappearance. In a way, a pulsar is more honest. It shows you exactly what it is, the ultimate matter crusher. Pulsars are not monsters hiding in the dark. They are out in the open, lighthouses we can see, measure, and study. They are completely and utterly unforgiving. They show us what happens when gravity almost wins the ultimate battle but stops just short of creating a black hole. If black holes represent the edge of our understanding of physics, of space and time itself, then pulsars represent the absolute edge of matter. They aren't the end of space-time, they are the end of matter as we know it. Thanks for watching.